3D. Please give him a round of applause one more time.
Some really cool stuff that I saw today. I'm really impressed. I don't know about you, but I'm really blown away by everything that I've seen. I'm really happy that I may join these people here and share my story. So what I want to talk about today is about, I have design background, design and mechanical engineering background, but since 13 years I've been working at a design office, and through the last years we've been evolving into a robotics company, robotics world, starting our own tech startup, and eventually coming to a crazy idea of 3D printing a bridge in Amsterdam. And I want to kind of share the ups and downs of a process like that. But before I start, I want to introduce you to this guy. I apologize for the very poor quality of the photo, but this is actually the best photo I could find of the guy. This is Nikolai Suchagin. He's a Russian entrepreneur, although some people say he's a crime lord, local crime lord. I don't know which is which, but I don't know him personally, but I do know what he did. I think in 1994, he had an idea. He wanted to build his own house. So he applied for a permit for a wooden house of 2 floors. And he started building it. And once he was done, he looked at his neighbor's house and he thought, my neighbors have a 3-floor building. He couldn't let it happen, of course, right? So he started adding another floor to his house. And then he thought, it's nice, 3-story, my house is a little bit bigger than the neighbors, but I want to go a little bit higher, I like the vantage point, I like to be able to see far away. So he started building another level on top of it. And he kept on going, and he kept on going, and he kept on going, until this came out, right? So this is actually a 45-meter high building, which is about 145 feet, I think. 45-meter high wooden building, which is the biggest wooden building in the world, single-handedly by one guy. Well, the reason I brought it up is there are some parallels between what this guy is doing and the way we work. And one of those parallels is that when he started building this house, he didn't know it was going to be that big, right? So he started building and he kept on adding, kept on adding. He had a new vision every time and he went for it. He just did it, went for it. And that's also how we work many times. So let me tell you what exactly it is that we do. We are a design company. We around Joris Laman. It's called Joris Laman Lab. I've worked with him for the last 13 years, I think. And we use new technology, new materials to make very high-end furniture that we sell through our gallery in New York. And we've been using 3D printing and lots of different types of digital manufacturing. For instance, this is a table. It's digitally manufactured. And the robot you see, it looks a bit like a lightsaber cutting through the table. But this is actually a robot that's spraying on a very scratch-resistant material on top of the tabletop. Because aluminium is a really soft material. And you don't want, when you put your plates or your glasses on your table, you don't want it to scratch, right? So you have to spray on this material. It's almost as hard as diamond. So you can imagine that this guy, it took him about 200 hours, man-hours, sanding the table. Actually, his name is Sander, so he's really fit for the job. But still, it's a long time, right? So another project I want to show you is the bone chair. This actually, and you've seen this with the former talks, Andre was talking about it, Scott was talking about it, Jason was talking about it. Topology optimization software. So this chair is done, it's called the bone chair. It was done in 2006 and it's actually mimicking the way that bones grow. And bones have the capacity to take material away where they don't need it. And obviously the car industry is really interested in it. Oh, sorry. Is this better? Car industry is really interested in it because it can make car parts more lightweight. And we were interested in it to see how nature would design a chair if you would let it. So you take a basic design space, put forces on it that you would expect on a chair, and then through many iterations you take material away up until the point that it breaks, and then you have the most efficient shape. So this was like 13 years ago, and it took about a week for every iteration. Right now it's one push of the button and it's calculating it, and so times change, you know, exponential. But then you end up with a render, and a render, you cannot sell a render, and we need to make some money obviously, so you have to produce it. And that's the first time we got in contact with 3D printing actually. We wanted to print the full chair in aluminium, because the shape is too complex to cast in traditional ways, right? But there were no printers that could actually do it. So instead we printed the mold. So on the left you actually see a sand mold being printed, or been printed. And we fill it with cast aluminium, and then we finish it, and a nice chair comes out. And this chair is actually in several museums all over the world in the collection. So, as designers, we have a little bit of a love-hate relationship with 3D printing. You know, on one hand, the promises are big. You know, you can do anything with 3D printing. But on the other hand, like 90% of the things being printed is stuff like this. You know, iPhone cases, and especially in the beginning of 3D printing, right? I mean, right now you see the companies like Enable printing prosthetics, and you see the Field Ready. They're printing actual, real cool stuff. And so what happened in the consumer-grade 3D printers, it's another exponential graph, you know, the price of consumer 3D printers, we already heard it today, it dropped dramatically. What we as designers would like to see is another line, you know, moving up with bigger building volumes, more materials, more choices, etc. So, but it's getting there, you know. I mean, the technology is really rapidly progressing, and so it's just a matter of time until these machines get more, can do more, etc. But we decided to do something with the shortcomings of the small machine. We bought a really cheap small machine that obviously couldn't print a full chair. So instead of that, we decided to cut up the chair. Actually write an algorithm that could cut up the chair into jigsaw puzzle pieces. So you can print all these pieces, you can change it, customize it, print all those pieces and put it together like a chair. And this is, for instance, Fab Lab, I think it was in Spain, and they downloaded the chair. They asked all of their members to put their name in it, print it in a different color, and then it all came together. Some crowds fabricated chair, and you can print it. So what we did was we uploaded the designs, and we made it free, available for download. So you could, this for instance, a children's chair. It's my daughter at the children's chair. We printed it especially for her with her name in it. And we made the designs freely available, freely downloadable online. Of the chair, obviously, not my daughter. But, so everybody with a 3D printer and some patience, because it's taken quite a long time still to print the parts, can print their own chair. You know, you can change the shape, you can change the color, kind of democratizing production techniques. So that's one side of the spectrum, right? The other side of the spectrum is this machine. It's a really, really cool machine. It can print really intricate parts. And really high level of detail, really, you know, high accuracy. It's a perfect machine. The only downside is, there's a few downsides. One is the price. A machine like this will probably cost you €500,000 €1,000,000. It's taking a long time to print, but for us, even more importantly, is the building volume. So this is a chair that we printed with it. It's designed all with generative design software, and this is an actual part. As you can see, there's a purple part somewhere here. That's actually this leg, one part of the chair. We had to cut up this chair into 16 different pieces in order to fit into 6 building volumes. So it's costing like 2 months to print one chair. So we thought there was room for improvement here. And we started talking to some 3D printing companies and asked them, can you please help us develop a 3D printer that can print large pieces, you know, furniture, pieces of furniture. But somehow none of them were interested. So we decided to take matters into our own hands and start developing our own printer. So what we did was we bought an old retired robot from the car industry. And together with two students from Spanish University, we developed this printer. And this is actually using a two-component, really fast curing urethane resin, which is mixed all the way in the tip of the machine. So you see two cartridges. These are just paint strippers from the hardware store to heat up the mixture to even cure faster. And we could print. And we found out that we could actually print structures starting from the wall. Because what's cool about an industrial robot, rather than the printers you've seen before, is that these are 6-axis robots. So the other printers, they have 3 axes of freedom, right? So they can only print inside a specific building volume. But once you have 6 axes of freedom, you can move outside of that volume. So we call that printing outside the box. And you can actually print starting from existing structures. You can print parts that are bigger than a printer itself, etc. So we were really enthusiastic about it. Downside is that the material, as you can see, is not really appealing. You know, you're not going to make high-end furniture with this. So we took it one step further. We thought, can we do the same trick with metal? So can we just take a welding machine, a MIG welding machine that's constantly adding metal to molten metal to another layer, and put that on the robot? And normally, you know, you use MIG welding machine to attach 2 pieces of metal together. But if you keep on going, you're essentially 3D printing, right? Brilliant, we thought. We were dreaming of early retirement. We thought we had golden hands until we found this patent online. It's almost 100 years ago. A guy named Ralph Baker had exactly the same idea, producing 3D printed parts with welding technique. Luckily, they didn't have software then, they didn't have robots then, so there was a lot for us to do still. It's not all was lost, so to say. So we started experimenting with it, we got better with it. First we used the 3 axes of freedom, soon we went to curved lines. Take some water. We started to print structures, which wasn't always easy, you know, things broke off. We had some issues in the workshop, trying to keep a clean workshop, you know, we had to swipe the floor. Some fires, started some fires. No big deal. I think we actually burned like 3 or 4 brooms in our workshop. But it happens, you know, you have to keep on working. I heard it today before, and nothing's more true. Keep on failing, you know, fail often and fail well. I'm not exactly sure what the exact quote was, but it had something to do with failing. Failing is good, you know. You have to fail in order to innovate. But, you know, before long we got better at it and we felt confident enough to actually print a design piece with it. So this is called the Dragon Bench, which is one of the pieces that from Joris Lauman Lab. We've printed about 7 or 8 of them. And the cool thing about it is that all of them are unique. You know, it's all unique pieces. And that's possible because in digital manufacturing, complexity doesn't matter anymore. You know, you don't need molds, so you can do everything. The robot doesn't matter. You just shoot it some information and it'll print it for you. So it got us thinking. You know, when we were printing furniture, we thought, what would be the next step? What else can we do? Can we take it? You know, can we scale it up? So we were looking at infrastructure, architecture, stuff like that. And by that time, we were on the radar of Autodesk, a software company. And they invited us to San Francisco to talk about a possible collaboration with them. And so the evening before we had the meeting, we were sitting in our Airbnb garden, drinking a beer, and we thought we need to think of something that's really going to blow their minds. You know, project we can do that's going to blow their minds. And we are from Amsterdam. Amsterdam is known for its canals and its bridges, so we knew it had to be a bridge. Because a bridge is, in order to print a bridge, you have to use a matured 3D printing technique. So there's no better way of proving that your technique is good enough if you can print something actually usable with it that has to hold a lot of people. So we were really enthusiastic about it. Luckily, they were enthusiastic as well. They said, "Okay, let us know when you have your ID worked out." So we worked out the ID, we sent it to them like, okay, this is the ID, this is what we're going to do. The idea was to start with 2 robots from each side of the canal and work our way to the center. And so the robots are basically printing the bridge, and the bridge would be the support structure itself. In the end, we had to kind of tune back our ambition a little bit because of different reasons. It wasn't possible to print on that location. The location is going to be one of the canals in the red light district in Amsterdam, and it's really, really busy there, so there was no chance, regulation-wise, to actually do it. So I spent quite a long time making this handwritten, hand-drawn animation. You know, I spent some evenings at home on the Lightbox drawing it. So you can imagine that I was a little bit pissed off when I get to the studio, and I said, "Look what I made," and my colleague showed me this photo. Sydney Harbour Bridge. Exactly the same. Thanks a lot. It's actually 1933. But what I think is interesting about this image, actually, is that it's, you know, this is also 3D printing, right? The image on the left is really a digital way. You're using robots to add metal. But, you know, the one on the right is also 3D printing. You're using cranes. It's very analog, but it's 3D printing altogether. So design-wise, it's also quite challenging, and it's really exciting to do. You have this new technique, you have this, you can do whatever you want. What are you going to do, you know? So we started thinking, we come up with all these crazy ideas for the design. We used the topology optimization software that you've seen for the chair. We came up with some very intricate shapes, but then we found out that there's, you know, there's also a limitation in regulation. What can you do? What can you actually, how can you prove that your bridge is strong enough? And the construction world is quite a traditional world, and it's very hard to come up with completely new ideas and actually get them validated and get them made. So we went through a lot of iterations, a lot of crazy ideas, a lot of crazy designs came by. And in the end, we went with this system where we are generating the stress lines within the bridge design, in the basic bridge design, and we translate them into more dense and more open areas. So we took the actual place where the bridge is going to be placed, so you can see it here, the canals. We made a 3D scan of the canal actually, put the bridge on top, put forces on it, and then the sea lines. And what you can see between this image and the next image is where you see a high concentration of red lines. You will see that the structure is more thick, and where it's more open, the structure itself is actually also open. This is a part of the actual part of the bridge. Well, not of the bridge is going to be placed, but one of the samples. And you can see the design here. So, you know, imagine where you can see the green part. That's roughly where this place is going to be. So you have an idea of scale. We actually made the design completely for that location. So we 3D scanned the canal and put the bridge shape on it. You can see the S shape in the bridge, right? That wasn't because we had to, but because we could. It made the design more interesting. So putting the forces on it, if you would have a straight bridge, it would be kind of boring, and we wanted to show what is possible with 3D printing. So we made an S-curve to make it a bit harder on ourselves, right? If it's easy, everybody does it, I think. But then, as said, you know, a bridge is a good idea because you're proving that people can walk over it. But in order to do so, you have to prove that people can walk over it, and that's quite complex as well. You know, there's regulations, a lot of regulations. It's a completely new material. It's a completely new technique. How are you gonna do that? You know, how are you gonna prove it? So what we did was, together with some partners in the industry, we decided to completely censor up the bridge. So we made a 3D scan of the bridge first, loaded it into the software, made a digital twin of the bridge, and then put all sensors on it, so whatever is happening with the bridge is also happening in the digital twin. And I think we did like 72 sensors, or at least that's what we started with. But because of budget reasons, I think it became somewhat less. And we censored it up, and then we did some real live tests. So that's also a difference between, it's actually going a little bit back to the traditional techniques, because you cannot calculate beforehand how strong the bridge is going to be, where it's going to fail, because you can only simulate the things that you know and not the things that you don't expect, right? So what we did was we put this actually concrete blocks and water tanks on top of the bridge, a total of 11 tons that we needed to make sure that about 100 people could stand on it or 50 people could jump on it. So that was the first test that we did, first in a series of tests. And all the sensors, they were measuring the deformation, vibration, etc. And here you can see with a drone shot what that looked like. And this actually proved that everything was well within the limits, and we were allowed. This was actually required by the city of Eindhoven in the Netherlands, because we were invited last October to place our bridge on the Dutch Design Week. So this was actually the first time that the bridge was fully assembled. We were really proud of it. It's like a few days before the opening of the Dutch Design Week, we welded these swirls on it, and it's the first time we saw it really come to life. So I want to show you a short video that we shot before and during that week. It shows the revealing of the bridge. So, thanks. So, we were rewarded the 2 Dutch Design Awards, one of which being the Public Award, which I think is the most important award to win. It means that people really like it. And the organization actually called it the selfie cannon of the exhibition, because all the people were taking photos with it. So it was really cool to see that it actually worked, and that it looked. People liked it as much as we did. So, for this bridge, there's one last thing to do, and that's getting a permit, right? Otherwise, we cannot place the bridge. So, right now we're in the process of getting a permit, which is a little bit odd. Normally, you start here, right? Before you start producing. First you get a permit, then you start producing. We didn't have time for that, right? So we couldn't wait for the permit. And I think that's the second parallel with Nikolai Sutjezin. Now, if he would have waited for the permit, this never would have happened, you know? No way he would have gotten the permit for it. And I think actually if we would have waited for a permit for the bridge, you know, I wouldn't be here, but I would be sitting at home, biting my nails, waiting for the permit, right? So there's no chance that it would have been done. So, you know, regulation sometimes is a killer for innovation. So you have to, you know, obviously it needs to be strong enough. We don't want to put a bridge there when it's not permit worthy, but we just couldn't go with the politics of it, and not politics, but kind of, you know, with the whole regulatory thing. And right now, because it's such a new project, it's very hard for the institutions, for the regulatory institutions as well, to find out how to judge if it's good and if it can be placed. So we're working really closely together with them to get this bridge done. So I also promised you a little sneak peek into the projects that we are going to do. So the bridge is going to be placed, hopefully by the end of 2019, the end of this year or the beginning of next year. So we will have some time on our hands to come up with some new projects. And it's a little bit the same as, you know, we have to put a new level on the building. And so we printed furniture, we printed infrastructure, bridges. So what's the next thing? Are we going to print complete cities? I don't think so, but we can do something to make cities maybe a little bit better. So in 2050, about 70% of the world population will live in cities. And you know, with that increase in urbanization, also the question arises, how are we going to keep this urban environment livable? And I think one of the things about a livable city, what you need is green. You need vegetation, right? So plants, trees, parks, etc. But you could also do that in green roofs, but also green facades maybe. So what we are working on right now is we are developing a robot that you can hang on the wall. Very simple robot with 2 simple anchors, or 4 simple anchors, and it can actually print moss on the wall. So moss or a substrate that makes it easy for moss to grow on. And as you can see, I locked myself up in my room again to make another hand-drawn animation. And moss is actually quite a remarkable organism. It can filter air, so it can absorb CO2, carbon dioxide from the air, fine dust from the air, so it can make the air a little bit cleaner. And what it can also do is it can absorb water. So when it's raining, it's absorbing a lot of water, and then when it's a dry period, it could release the water, vaporize the water, cooling down the city a little bit. So by doing that, you could reduce the urban heat island effect a little bit. That's the effect where in cities, inside cities, urban areas, the temperature is 4 to sometimes even 7 degrees Celsius higher than outside in the rural areas. And obviously we're not saying that, this printer is going to solve all of that, especially not if you have one, but think exponentially. What if you have a whole army of these printers printing whole cities green, right? What would happen then? It's interesting to think about. So right now we are working on a prototype, the first prototype for this, and I filmed this, I think 4 or 5 days ago. It took us about 3 months, smart intern, and 3 months time to make this. It's a very first version that's just drawing some lines on the wall, but we are trying in the next 3 to 6 months to come up with a real prototype, working prototype that's actually printing the substrate on the wall, and start greening the cities. And then before you know it, a building like this could look like this, right? You could make green patterns on it, or take it one step further, concrete facades. The whole world is full of them, cities are full of them. They might look at this like this at a certain time, right? It's keep on dreaming, right? So, yeah, that about concludes my talk. Thank you very much for your attention, and I wish you a lot of pleasure in the next lectures, because I think there's a lot more really cool stuff to come. Thanks.